Hello everyone, welcome to the first recitation of 122 Fluid Mechanics in fall 2025. This week we will have 6 different questions and they are relatively easy. So let's get started with the first one. The first question is about density. So if the density rho of air increases by a factor of 1.4x due to temperature change, what will happen? We have three options. Specific weight increases by 1.4, increases by 13.7, or specific weight remains the same. So this is actually very easy because the density is a dimension of m over cubic L. So we can either have kilogram over cubic meter, or it can be pound over cubic feet. So there is a relationship between specific weight and density. So specific weight is equal to density times gravitational acceleration. So since this is going to be constant, and if we increase this value by 1.4, therefore we will see an increase by 1.4x in specific weight. Okay, let's continue with the second question. This is question 2.12. So we need to find dynamic and kinematic viscosities of kerosene, motor oil, and water at temperature of 50 Celsius. So let's first find the location of 50 Celsius. We can see it's almost here. So that we can match it here. And then we have motor oil. And we need to find the intersect of this line and curve of each material. So we have motor oil here. For kerosene, we can take this line. And we have water, which is almost here, we can say. So for motor oil, we can take 5, or let's say 4.5 down to the power of -5. And for kerosene, we can get something between 1 and 2. So let's assume it is 1.5 10 to the power of -6. And another one is water, and it is almost between 5 and 6. So let's say 5.5 times this time -7. Okay, now continue with dynamic or absolute viscosity. Similarly, we are going to draw 50 Celsius line, which is here. And then we have curve for motor oil, we have kerosene, and we have water here. So let's say this is for 4 times 10 to the power of 2. For kerosene, we can say 1 almost. And for water, again, it will be between 5 and 6, and let's say 5.5 10 to the power of -4. So you can actually get exact values in table A.5. So let's write again everything. We have kerosene, and finally we have water. Okay, we can continue with question 3. This is 2.20. Dimensions of the bulk modulus of elasticity are the same as the dimensions of pressure, density, pressure and volume, and only pressure. So we have bulk modulus of elasticity, and you can find the equation of bulk modulus in equation 2.4, so that we have minus delta P over minus volume over volume. So this actually means that we have a change in pressure and fractional change in volume. So this is just a fractional change in volume, so that this will be dimensionless. So the final dimension of bulk modulus will be change in pressure. So since we have pressure as Newton over square meter, the dimension will be same as the pressure. So the answer is C. Question for now, it is 2.47. A water column in a glass tube is used to measure the pressure in a pipe. The tube is 1.5 inch diameter, and how much of the water column is due to surface tension effects? And what would be the surface tension effect if the tube were 1/8 or 1/16 inch diameters? So let's assume this is our tube, and we are using it to measure pressure. And as you can see, we have a water column here, and this is actually happening because of the capillary rise. And to calculate the capillary rise, we can use this equation, delta H, which shows the rise in this tube, so that it will give the water column. We have 4 surface tension of water over gamma d. So we have specific weight, we have diameter, we have surface tension, and they will all give the capillary rise or water column. So from table A4, 8.4, you can find the value of surface tension for water. So it is actually 0.005 lbf over feet. So here we have 4 times 0.005. And below we have specific weight of water, which is 62.4 lbf over cubic feet, times we have diameter, which is in feet. So this is going to give 3.21 times 10 to the power of -4 square feet over d. So that we are going to just replace these values to find the effect of surface tension in each tube. So for 1/8 inch, and this is actually 1/96 feet. We are doing that because the diameter is a unit of feet, and actually all other values has feet, so that we are going to continue with feet. So from here, delta H is equal to we have 196 feet. So as I said, we are going to use this final equation for all of these cubes. So we have this for 1/8. For 1/16 we will get 1/192 feet. It will be equal to 0.0615 feet. And for this one, it was 0.308 feet. And we can get this in inches. And this will be 0.739 inches. And finally, we can get half inch, which is 1/24 feet. And from here, delta H will be 0.00769 feet, which is equal to 0.093 inch. So we have all of the values we need. So basically, the surface tension is making this impact, and we can see these values of water columns in each different tubes. Okay, now question 5, 0.16. We have a closed tank, and we had some gauge stepped into it, and we define specific rate of the oil and the pressure reading on gauge C. So in this type of closed tanks, we will have a very simple calculation because, for example, at this point, this pressure will be equal to pressure above it. And for example, for PC, it will have pressure above it. So we will consider all of these fluids and specific weights so that we can finally get pressure at C. So let's get started with the first question, which is specific gravity of the oil. So as I mentioned, we have PB here, and we defined specific gravity of oil. So let's first write this equation. We have PA plus this height, which is 1 meter, times specific weight of oil. The main reason for writing this equation is that we need to find specific gravity, and to find specific gravity, we can actually use this relationship, which is specific weight of oil over specific weight of water. So using these pressure relationships and equations, we can get specific weight, then we can reach the specific gravity value. So as I mentioned, for PB, which has 58.5 kilopascal pressure, it will have the pressure here. Since this is here, it will not have a hydrostatic impact on here, so we can directly get this value. So it will be PA plus this height. It will be equal to pressure B. So let's say PB plus gamma, and let's say ZB, which is the height of B. But since we are at the level of B, we can assume this as 0. And for PA, we have 50,000 Pascal, Newton over square meter, plus 1, and we have specific weight of oil, which will equal to 58,500 Newton over square. So here you can either select kilopascal or Pascal. The result will be same. And this is going to give specific weight of oil as 8,500 Newton over cubic meter. And using this first equation, we can calculate specific weight of oil as 8,500 over 9,810 Newton over cubic meter. And this is specific weight of water, and this one is for oil. Therefore, we can get specific gravity as 0.87. So this is the first result for specific gravity of the oil. And then we need to go second solution, which will be B, and it actually asks PC. So pressure at point C. Again, we can do the same approach. So PC will be, PC will be equal to, we can start from B, PB plus this small height, which is 0.5 times specific weight of oil, plus we have another water column, which is 1 meter of water. So it's not another, it is 1 meter of water. So that we will have specific weight of water times 1 meter, and this is also 1 meter. So here we only take this value because we don't need to know upper side, because this is actually equal what we have here and here, so that we can directly continue with this known value. So we don't need actually do these calculations. So if you continue from here, TB is 58,500. Of course, this is Pascal, plus 0.5 times 8,500 Newton cubic meter, plus specific weight of water times 1, which is the water height. So from here, we are going to get 72.560 Newton over, Newton over square meter, or we can say 72.6 Newton over square meter. So this is Pascal, and this is kilopascal. Okay, this is the final question, 3.37, and we need to find the pressure at the center of pipe B. So we are going to use this manometer, and we have PB, which is pressure at B. And let's say we have point A here, and we will have PA. So to simplify calculations, if you remember, we have these equations. So for example, if we are coming from A to B, when we are going down, we are going to get positive values. and the pressure is equal to specific weight times height. So when we are going up, we will get minus values. So it will be, the pressure will be same, but this time we will have negative values. So let's say up. And also, this manometer is open to atmosphere at A side. So we can basically assume that PA is equal to 0. So let's get started from A to B. We have PA. We will have this much down. So we will have 70 centimeters, or it is going to be 0.3 meters. So let's say we have 0.3 meters times the specific weight of this first fluid, which is 20 kilonewton over cubic meter. And now we are going to up, and we have this small portion of the first fluid, but since we are going up, it will take minus, and it is 10 centimeter, which is 0.1 meters times. Again, since it is still the same fluid, it will be 20. And let's keep going from this level to pressure B. So we will have minus because we are going up, and the height is 0.5 meters times 10 kilonewton over cubic meter. And if you do all the calculations, we are going to get minus 1 kilopascal pressure. Or in other words, it will be minus 1 kilonewton over square meter.